Hello everyone, in this video I will explain you Kirchhoff's rules. They are two rules that will allow you to analyze any given circuit in terms of voltages, currents, resistances, whatever is needed. So there's two of them. The first one is based on the conservation of charge. It says that if we have current coming into a junction point here, the sum of incoming currents must equal the sum of outgoing currents. So for example, if here we had I1 and this would be I2, because charge is conserved, the I must equal I1 plus I2. And also it applies the same thing here. Now the incoming ones are I1 plus I2, so they must equal the outgoing current, which is of course the same one that is leaving the battery, that will go into the battery, like this. Same thing in writing. At any junction point, the sum of all currents entering the junction must equal the sum of all currents leaving the junction. So this was just based on the conservation of charge, which means conservation of current. The second one is based on conservation of energy, and it has to do with voltages. So here we have a 12-volt battery, and the circuit branches into two different loops, if you will. The second Kirchhoff's rule says that the change in potential in any closed loop must be equal to zero. So pretty much what it says, that if you start from here and go around, you must come to the same point or the same potential value. So for example, in this loop, let's go in this direction, the lower loop. We start from here. We can say that this is 0 volts. And when we jump over the battery, the voltage increases to 12 volts. It's 12 all the way here. And then it drops 8 volts over the first resistor. So we go from 12 minus 8 to 4. And then over the second resistor, we drop from 4 to 0, because here we drop 4 volts. So we have 0 here, 0 here, 0 here. So we started from 0 and came back to 0. Good. Now the same applies for any closed loop. So there was one closed loop. There's another closed loop here. So the upper one also, let's go in this direction. So we can start any random point. So let's start from here, for example. So whatever the value here is, let's call this one 0. So 0, we drop 4, we go to minus 4. And then here, minus 4, we jump up 12, we go to plus 8. Plus 8, plus 8, plus 8, plus 8. Drop 8, come back to 4. And we have one more loop in this system, the big one. So starting from here, let's start here. So here we have 12 volts, for example. 12 volts, 12 volts, 12 volts. We drop 12 volts. We come back to 0, 0, 0, 0, 0. And then we jump over the battery. We gain another 12. So we come back to 12 where we started. And here's the second rule in writing. The sum of changes in potential around any closed loop of a circuit must be 0. But how do you know when does the potential increase or decrease when you go over a resistor or a battery? So let's have a resistor here. And we have guessed that the current goes this way. So we don't even have to know the actual direction of the current, as long as we guess it and stick to that convention. So we are saying the current goes this way. So in this case, the voltage must drop when you go with the current. Like in these cases, the current was coming in from here and it was dropping with the direction of the voltage arc, which is based only on the direction of the current. So if we're moving from here to here, along with these arrows, then the voltage is being dropped. And in fact, we don't even need this arrow. We can just say that there is a voltage drop, but we don't know in what direction necessarily. So whenever we go in the direction indicated by the current, the voltage will drop. On the other hand, if we would complete our loop in such a way that we would do something like this, go in this direction, then because we are going against the current, then the voltage would increase. And for battery, there's always a positive and negative terminal, and the voltage is higher on the positive one, so positive and negative. So the voltage arrow looks like this. So again, when you're going against the arrow, the voltage increases, and when you go to the direction shown by the arrow, the voltage drops. So these arrows, when we indicate them like this, they mean a voltage drop in this direction. So in this case, it would indeed be in this way. The voltage drops in the direction where the current is flowing. Here we have an actual example of what we just discussed. So we are supposed to write the equation for the lower loop, ABCD, so which means going ABCD, which means going in this direction, and show, assuming the currents calculated in this example, that the potential really add up to 0 for the lower loop. So the first part of this example, they got the following currents. So I1 was minus 0.87 amps, I2 was 2.6 amps, and I3 was about 1.7 amps. So here's the example when they decided that I1 would go in this direction, but if you perform the calculations based on the loop analysis, it turned out to be negative. So this means that the actual direction of the current in here is going this way. But this just indicates that it doesn't matter what you pick, the calculations will eventually tell you if you were right or wrong. Right. So, but back to our case, so we want to start from point A and then go clockwise in this loop. As we do that, the first obstacle we encounter is this 40 ohm resistor. And because we're going against the current, the potential will rise. So we have plus I3 times 40 ohms going from A to B. Then going from B to C, again we go against the current, which is the same I3. Resistance is just different, so again we add potential or voltage times 1 ohm. And now we are at point C. And when we go across the battery from high to low, we drop voltage. So we drop 45, so we have to subtract 45 volts. And now we are at point D. And what's the current through this resistor? It's I2 going all the way, so the same I2 is here. So we're going against the current again. So we add up or add voltage. So I2 times 20 ohms. And then we come to point E, and then again we go against the current. So and the I2 is flowing here, so we add I2 times the resistance 1 ohm. And now we only have the battery left, and we are against going from high to low, so we are dropping we are dropping 80 volts, so we have to subtract 80 volts. So what is the value of this expression? So let's simplify a little bit. So we have I3, we can combine those two. So I3 times 41 ohms, adding 40 and 1. Then we have minus 45 volts. And then I2 we can combine plus I2 times 21 ohms. And then we subtract the 80 volts. So if we plug in these values, so this is 1.7 amps times 41 ohms minus 45 volts plus I2, which is 2.6 amps times 21, and then we subtract 80 volts. We get minus 0.7 volts. But this is only because we dropped some decimals out of these current values, so if you do them with accurate numbers, you will indeed get 0.